So in this video, we're going to provide an overall motivation for the content in Chapter 7 and also do an initial example problem. So thinking back to Chapter 6, we predominantly talked about two different techniques in order to solve for whether or not an actual member inside a truss was in tension or compression. The two techniques that we talked about were the method of joints and the method of sections. If you remember the analysis technique associated with the method of sections, the way that we actually expedited the solution was to actually divide the truss in such a manner that we passed a segment through the middle of a lot of those different members of the truss. So what that was really showing is that those forces that we were solving for, tension and compression forces that were present in each individual member, couldn't only be viewed as kind of external forces to the actual member themselves, but they were also internal to the members, particularly when those loads were subjected on the truss overall. What that actually did was kind of induce a stress inside each of the members of the truss. And that's probably not surprising to you that when you're designing some type of load-bearing structure, what you really need to be considerate of is how the external load that is present on that, whatever the structure may be. In this case, if we look at the billboard to the right, we not only need to consider the loading effects of the weight of the billboard itself, but also whatever kind of external perturbations it might act on the billboard. Like, for example, if you had a very heavy wind gust, there's a lot of surface area that's going to have the capability to capture a big bending moment, kind of about an excess of the actual supporting column. So long story short, when you design a supporting structure, you have to be considerate of the internal forces of the various components of the supporting assembly. And even though in Chapter 6, when we actually were able to analyze the internal tension and compression of the various members of a truss, which were modeled as being infinitesimally thin, we know that in the world around us, when we observe actual support structures, it's very common for the cross-sectional area of those support structures or their various components to not be uniform across the entire kind of duration or span of the member. And an example of this is actually shown on the right, where we have a column that's serving to support this billboard. And if we notice clearly, the cross-sectional area is not uniform across the entire column. So what we're going to be kind of covering in this chapter is a general technique in order to solve for the internal, we'll just call them stresses at this point, that are present within members of a load-bearing structure, kind of based upon doing analysis of the overall structure. And in order to do that, the initial thing that we need to do is to talk about a general model for describing the types of internal forces that are present inside each of those support structures. So we're going to use an approach where we're going to kind of lump all of the individual stresses into just a set of three forces. And the first force is one that we're already familiar with. So if you take any kind of member inside a load-bearing structure and you just break it in half and you look at the entire cross-section, one thing that will be present that we need to have within our model of the internal forces is a force that's normal to that surface. And what that is going to describe is the kind of existence of a stress in there that's describing how much that member is either being compressed or placed into tension. And then we're familiar with that, of course, from the analysis that we did of trusses. In addition, if we look at that cross-sectional area, there needs to be a lumped force that's actually not normal to the surface, but parallel to the surface. And what that is going to describe is the tendency of a given load kind of on the overall structure to cause that individual member to kind of slip each surface area relative to one another in the other direction. And you're probably familiar with from your physics course that phenomenon is actually called shearing. So that force that's present internal to the members that is parallel to the surface area is often referred to as the shearing force. In addition, we know that when we have some type of structure that's load-bearing, the individual members can kind of bend. So describing that stress is going to require a moment, and that is referred to as the bending moment. So if you look at this kind of diagram that we have to the right, those three forces are present. A force that is normal to the cross-section, that is called the normal force. One that is parallel to the cross-section, which is referred to as the shear force, and the actual bending moment. And those three things collectively describe all the different types of stresses that can occur inside the member of an actual load-bearing frame. One thing that I want you to be aware of is that we've naturally assumed some type of sign convention when we actually did the segmentation. So we only are seeing the left portion of in this case, kind of what looks like a beam that we've cut apart. But remember, by Newton's third law, there's also a right portion where each of those internal forces exist, but they satisfy the conditions of a reaction pair. Meaning that if by convention we segment a beam and the portion on the left, we show the shearing force as going in the downward direction, the portion on the right would have a matching shearing force in the upward direction. And that same ideal would, of course, apply for the normal force. It needs to be equal and opposite. and the bending moment. So just be aware that there is kind of a sign convention traditionally employed when you actually analyze and attempt to determine the internal forces inside a member. And we'll talk about how you actually do that in a minute. But if you think about it, it's probably based upon the fact that if these are some forces we don't know, if we just take some body that we're analyzing through static-based analysis, and we actually draw a free body diagram, and we segment a member such that these three unknowns are present, in a two-dimensional problem, that's already three unknowns. So in order to be statically determinate, we don't have the ability to solve for any additional unknowns. So just solving for these forces is going to, these internal stresses, which two of which are forces and one of which is a moment, is going to kind of max out our ability with respect to the equations of equilibrium that we can write. So it's probably not surprising to you that the first step in solving any of these problems, like for example, looking here on the right, if I were actually interested in determining the internal stresses here at point B, if I were to draw a free body diagram where I segmented the beam at point B, and I were to include my model of my three internal stresses, the shearing force, the normal force, and the bending moment, that's already three unknowns. So I don't have the capability to solve for any additional unknowns in kind of a two-dimensional static equilibrium analysis. So the first thing that I'm going to do is have to solve for any external reactions before I actually do my segmentation. And that's all that this first bullet point is telling you, that if you're interested in solving for the internal stresses at point B, the first thing that you need to do is do an analysis of the entire beam in order to determine these reaction forces. In the case that these are pin connections, of course, they have the capability to induce both horizontal and vertical reactions. But if there's only a vertical loading and a moment loading, those horizontal reactions aren't going to be necessary. So in terms of the workflow of analyzing this, I segment it from the actual support structures. I solve for the reactions, which are going to be purely vertical in this case. Once I have those two, I can actually draw a segmentation of my beam at the point at which I'm interested in determining internal forces, which is point B in this case, and I can add in my model of my shearing force, my normal force, and my bending moment using the sign convention that I showed in the previous slide. So let's actually take a look at how you would do this. If I'm given a distributed load on a beam that's uniform density of 3 kip per feet, and I'm interested in finding the internal forces at point C. Well, how am I going to do it? Well, remember the internal forces at point C, even if I were to draw a free body diagram where I segmented the beam at that point, whether I consider the left portion of the beam in equilibrium or the right portion of the beam in equilibrium, and they both have to be, but whichever one I pick to solve for the unknowns I'm interested in, I can't have any additional unknowns besides those internal forces because there are 3 of them and I can only write 3 equations of equilibrium. So the first thing that I'm going to have to do is to solve for the actual reactions which are occurring at A and B. A, we have a roller support. B, we have a pin support. The roller support, of course, can only induce a vertical reaction. The pin support can induce both a vertical and a horizontal reaction. But before I actually solve for the internal forces at C, which is going to involve choosing which portion of the beam I want to work with, I have to find those reactions. And if you notice, that's exactly what we've done here. I've segmented the beam from its support structures. I've replaced the 2 reactions by equivalent forces for the type of force, kind of opposition force that they can actually supply in this case. I've replaced this distributed load by a single equivalent load. Remember that the magnitude of the force of that equivalent load is nothing more than the area under this density. If it's 3 kip per feet and it's distributed over 6 feet, since it's uniform, that would be an 18 kip force. Since we have uniform density, it's going to be applied directly at the midpoint of that density. So that will just be 3 feet from the end of the beam. And if you notice in this case, I have my unknown reaction AY, my unknown reaction BY. Your book's being a little unconventional here of choosing BY to go in the downward direction. Usually we would just choose them both to go up and we would let the math work itself out. But knowing that when I actually draw my segmentation and show my internal forces at C, then I'm only going to work with the section of the beam that's to the right. The way that what I'm going to do is I'm just going to solve for the reactions at B, because the ultimate free body diagram that I'm going to analyze isn't going to involve AY. So how could I solve for the reactions at B? Well, very clearly, hopefully everyone sees that since there are no other horizontal forces acting upon this beam, that Bx has to be 0. That's all that's being showed there. And if I don't know AY, if I sum all the moments about AY, meaning I'm going to pin it there, we notice that the 18 kip force will induce a counterclockwise rotation. That is going to be about point A. That will be positive. And the reaction here at B, if you draw it in the convention that the book has drawn it, that's going to induce a clockwise rotation, which would be negative. So that's why we have a negative sign in front of the unknown reaction by. Note that relative to point A, the perpendicular distance is 9 feet. That's how they're determining the 9 here. We don't know by. Negative because of the way that they're showing it. It would be a clockwise rotation. And then we know that this 18 kip force, as I mentioned again, is going to induce a counterclockwise rotation. And relative to point A, it is 3 feet separated. So I can solve this for By. And what I determine is that By has to be 6 kips. And since we've obtained a positive result there, that shows us that the sign convention that we assumed in the downward direction is actually right. So what did that buy us? Now that I know the reactions of Bx and By, if I actually segment this body, I segment this beam, and I only show the portion to C and to the left. When I make that segmentation, all that I have to do is add in my internal forces. Now note, why are they picking the sign convention that they picked here? Remember that by convention, when you segment a beam, we'll have the portion on the left have a normal force that's going out to the right, a shearing force that's going down, and a bending moment that's going counterclockwise. So if I consider the surface area to the right, using the same sign convention, remember that by Newton's third laws, the reactions have to be equal in magnitude but opposite in direction. So the shear will go up, the normal will go to the left, and the bending moment, where we're at, will go in the counterclockwise direction. And that's exactly what we have going on here. So this is a statically determinate problem. If we look at it, what do we need to do? Well, if we only have one reaction load, which we know, which is 6 kips, if I sum all forces in the horizontal direction, since there are no other horizontal forces, what that tells me is that this beam is not in tension or compression, namely the internal stress corresponding to the normal force, NC, is 0. If I sum all forces in the vertical direction, all that will tell me is that the shearing force is equal to the equal magnitude and opposite direction of this reaction. So it's going to be minus 6 kips according to the sign convention that I've shown here. And the last thing that I need to do is to determine the moment, this bending moment, MC. And the way that I can do that is to simply sum all moments about point C. If I sum all moments about point C, what I will have there, if you think about that reaction applied at B, it's going to induce a clockwise moment, so it will be negative. The magnitude of the force is 6 kips. Perpendicular distance is 4.5 feet. So this first term is just showing you how the reaction at B induces a bending moment about point C. And by our sign convention of using counterclockwise positive, of course, the internal bending moment that is opposing that will be minus MC. And if I solve, what I will find is that MC is actually minus 27 kip times feet. And that is just showing you how this reaction at B, which was determined in order partially as a function to counterbalance the applied load of distributed 3 kips per feet over on the left side of the beam, how much bending moment or tendency to bend or stress is being induced in the beam at point C. So a lot of words, it sounds really confusing, but hopefully when you work a couple of these out, and we're going to look at a couple more examples, one based upon an actual problem just from a PowerPoint, but I'll also work kind of to give you a starting point on a couple of your homework examples during this first portion of the Chapter 7 lecture as well.